Hello students, let me derive the Maxwell's equation when the field is changing with time, that means the time varying electric and magnetic field. So when we have the time varying electric and magnetic field, there will be the change in the equation number 3 and 4 of Maxwell's equation. So let we see the third equation, how does it get modified. So the third equation is derived on the basis of Faraday's law. So the Faraday's law is about the generation of electromotive force. So but when the fields are changing with time, in that case there is a change in the flux that generates the electromotive force. What does we call that? The electromotive force, which is nothing but the work done. We define it as the work done in moving a unit charge around a closed path. Okay, so let's see when the fields are changing with time, how the equation number 3 changes. So basically our equation number 3 was the curl of electric field is equals to 0, because the work done in moving a charge around the closed path in the static field is 0. So that is how we got this equation. In static field, the work done is 0. But when in varying field we have time varying field, the electromotive force we write as the rate of change of flux with time. This is how we write the electromotive force equation. I am defining the electromotive force by E. Okay. Now the electromotive force is the work done in moving a charge around a closed path. So the work done is given as F dot dl. You must have seen the force multiplied by the displacement. So we usually write it as Q1 Q2 over 4 pi epsilon naught r square in terms of electric field if I am talking about. So dot dl. So right now if the charge Q2 is a unit charge, so this simply is equivalent to Q1 upon 4 pi epsilon naught r square dl, which is equivalent to the electric field. That is, electric field we define as the force per unit charge. So simply the work done can be written as E dot dl in place of F dot dl. I can write it as like this, and if it is around the closed path, then I can write it as the integration over a closed loop. So now the equation number 1 and 2 are equivalent because the work done is equivalent to EMF. So from 1 and 2 I can write minus del phi by del t, the rate of change of flux, is equivalent to integral E dot dl, that is the electromotive force we have compared. Now the flux, the magnetic flux, I should define it by B. The magnetic flux is equivalent to B dot ds. We define it as, where B is the magnetic flux density, we define it as magnetic flux density, ds is the surface integral we have taken here. So right now let me give the name to this equation, say 3. So in place of phi I can put B dot ds. So the equation number 1 becomes minus del by del t integration B dot ds equal to integration E dot dl. Okay. Now if you see the equation, the left hand side is the integration over surface, the right hand side is the integration over, this is the line integral. So this is 2-dimensional quantity, this is 3-dimensional quantity. So let me convert them into same dimension. So by using Stokes theorem, I can write B dot ds, this can be written in terms of, this can be written as the left hand side can be written as the in terms of curl, not this one, the right hand side. Integration E dot dl I can write as the curl of E over the surface integral I am taking. Okay, so now this equation number 4 I can write as curl of E, the integration over the surface over the closed path, is equivalent to minus del by del t integration B dot ds, that is already there in the left hand side. So let me combine the two equation, the curl of E plus del by del t V, the integration, the surface integration is taken equals to 0, or the differential form is simply the curl of E equals minus del V by del t. So this is the modification in the equation.